Oi, Dissecting Multiplication in Transformers. This paper, if you've been wondering why the heck language models ChatGPT are so wildly bad at some very simple tasks like multiplying, like they just cannot do simple math, this paper has a great explanation for you. Also, if you're just generally into mech this is a good explanation, shows the attention patterns when doing multiplication. All around interesting paper, really calls into question the difficulties that happen when you have this combination of specific architecture, specific training type, and specific way in which we record data in the English language, which may also not be the case for other languages, but whatever. Anyways, I think you'll like it. I thought it was pretty cool. I suppose let's get into it. Before we start, remember to like, subscribe, comment, share, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, support me either through Patreon or YouTube. For as low as $1 per month, you can get early access to my videos, or for a one-time payment, hit my Venmo. And if you'd like to borrow my brain for an hour or two, book a consultation call. All links are over on my link tree. Let's get started. Disclaimer. So there's this issue in the field where we have this huge disparity between some tasks that we would assume are more complicated, the LLMs are very good at, hence like natural language, right? But other tasks that we think of as very simple are the opposite. They are not very good at them. In particular, this paper we're going to do multiplication, just like many digit multiplying, right? And this is actually a recurring theme in AI in general, is we tend to, as researchers, assume, not me yet, but whatever, we tend to assume the difficulty and easiness of a task uh, almost based off of like our own subjective sense of difficulty, which is generally very misguided. For example, a lot of like the robotics once upon a time in like the 50s or whatever it was thought of to have probably been easier, whereas now we're finding that like complex reasoning uh, is the easier thing and robotics is the more difficult thing, right? It seems like we tend to overestimate how impressive and difficult the things that our minds are capable of doing that other animal minds are not capable of doing, and we underestimate the things which animal minds can do that we cannot do. We really underestimate how complex evolution is in its ability to solve tasks and the complexity of solutions it has created. That's a more at broad, but it applies even here to thinking about like multiplication versus natural language. You would assume, especially given that like computers can do multiplication, right? You would really assume that would be better, easier for an AI to do as well. But just these systems really do work very differently from regular computers, and so we actually have this very odd shortcoming, right? Now, there's a couple reasons for the difficulty in this specific task. First up is data format. We actually have sequentially arranged characters, right, in NLP, meaning that the models have to read these the words, the tokens from beginning to end, and they don't get to do any reordering like we get to do. Models are very much beginning to end machines. They cannot reorder things. And interestingly, in arithmetic problems like multiplication and addition, the calculations are actually a bit out of order, right? If we were to have the ones digit go first and then the biggest digit of the number go last, this task would be a lot easier for AI models trained on next token prediction to do. But we have this kind of reverse setup where the model basically has to calculate the entire number all in one token go, and then it gets to iteratively output the answer to that, as opposed to we'll get into the actual algorithm later. But anyways, the next one being an intermediate step. Um, some tasks out there are just literally there is one thing to do, right? But arithmetic, especially multiplication, has a very like a series of intermediate steps. You have to multiply every single digit with every single other digit, and those compound on each other, hence carrying over digits, right? And there is a uniqueness to this task and to the tasks that regular computers are good at in general, is that in NLP, in natural language processing, with language, there is generally a probability distribution of possible correct answers. Whereas in computer type, like the tasks that computers are usually good at, they're generally very difficult, not difficult, but they are hard coded, correct single answers, right? So the model is used to outputting probabilities over every single digits, every single number in its vocabulary. But then when it comes to actually doing math, suddenly you don't want chances. You want a hard and fast correct answer and a hard and fast knowledge that everything else is not correct. And finally, just lacking in data. Um, this is an odd one that they proposed as a difficulty. Proportion of arithmetic data in an internet collected training data set is low. Is it really? I'm not quite sure about that. I mean, I feel like it happens all the time, just in language, in whatever PDF you might read. Although I will say, most calculations that happen throughout I don't know, a report of some kind or something, are very many steps, many implicit steps that are skipped past, right? Whereas models really do benefit from you showing them every single item in the task. So what they're referring to, I bet, is a serious, actual, comprehensive breakdown of every single subtask would be the goal, and that is what is lacking in the actual training data. So the actual tasks being performed today, right? First up is M refers to multiple digits in the multiplication, and U refers to a single digit. And then we have different combinations of them. So, for example, this big number times 2 equals this big number, right? They also test reversing the final answer, right? So, same problem, but they say, does the language model, or does the, sorry, transformer find it easier if we reverse the order of those numbers? We start with 4, end with 1, instead of starting with 1, ending with 4, right? And then those two are the easier ones. Multiplying by a single digit number isn't that bad. Whereas the more difficult task is m by m multiplication, aka big number times big number, right? And then they also have a reversal version of this same big number by big number task as well. The idea being, does the model have an easier time given that it only has to do the ones digit first, and then it can think of the tens digit, etc., right? Now, when thinking about what this task actually is, we're going to look at first the big number times small number task. They assert that the transformer utilizes several basic subtasks to complete this multiplication, right? First one is base multiply, which pretty simple. It just finds the product of two single digits. Next one is the carry over, which, as it sounds like, responsible for the carrying over of the digit onto the next digit, and then use carry. So while one part of the carry, like one carry task, is to tell the next digit setup, hey, here's a digit to use for you. Let me actually show you all. I'm referring to, if you're forgetting, multiplication, right? These little tables, you have to carry over the digit if it gets too big, right? That should be obvious, but just in case. So for subtasks, when you're actually doing the carryover, there is one task that is uh, calculating the carryover from the previous digit, and the next task is actually remembering or deciding to use that carryover digit from the previous digit multiplication. And now, interestingly, those were all subtasks, right? But we can then kind of combine them and label them. The one of interest today is called use carry and further carry, UCFC, which considers the carry from the previous column and further produces carry to the next column. Meaning it does the look at carry, right? It looks at the carry from the previous one and then decides to use it. And it then calculates the carry, and it does a base multiply for its actual digits of interest, and it calculates the carry for the next column. So that is a combination of all three. Very interesting here. They can actually split up the loss curves into per task loss curves. Up left, we have the overall per digit loss curve. And then here you can see certain tasks are faster. So the just multiplying without the carrying is really quick to learn. When you add on the carry task, it becomes harder. The just carry task, so C right here is a combination of tasks. The just carry tasks is difficult, obviously, and then the use carry task is delayed from the carry task because you can't use the carried over digit until you already have said digit to carry over having been calculated. And then same thing, the big compound UCFC task is even further delayed. The transformer actually has to learn these tasks in order. This, if you recognize this, is huge in terms of thinking about this in terms of grokking, right? When language modeling, there are probably a lot of tasks that cannot all be learned at once. And so a big speculation with grokking is that the model actually, when doing language modeling, a many task setup, the language model probably is constantly learning new tasks and constantly grokking and having to only continuously learn tasks that themselves are compositions of prior tasks or are only capable of being done once a prior task has already been grokked, right? Hence why we don't see grokking in full-on big language modeling. Instead, we see a smooth loss curve, and yet we still see sudden emergence of abilities. You can kind of think of this in the same way, or it actually is the same thing, is it seems like certain tasks come after one another and in a specific order. Hence the whole sudden emergence of specific abilities despite smooth loss curve decreasing. Furthermore, we also see that the UCFC's loss curve is much noisier than the others. Look at this. Most of these curves, that's the level of noise they have. You look at UCFC, boom, very noisy in comparison, right? The reason being that calculating the UCFC spans 3 digits, so inaccuracy in any one single digit in any one single task will force an error in the UCFC task, right? So if you have a whatever percent error rate in each of the 3 subtasks, then those effectively combine on each other, not to mention the fact because they prevent the UCFC task from being applied correctly, not to mention the actual circuit implementing those combined tasks together itself has its own error rate on top of that, right? Hence the much more noise in the loss. Now here in this table, they did a comparison of the regular order, regular, they call it ordinal, of the answer versus the reversed answer. Reminder, that was this piece right here. And normally in just human writing, we do the biggest digit first and we end with the ones digit. They wanted to see if the model had did better doing the ones digit first and then increasing the actual digit, which is important because in order to get that first digit in the way we usually write things, we need to effectively calculate everything beforehand, right? When humans write this out, this one first, then this one, then this one. So by reverse ordering, we're effectively helping the model, given that it is a next token predictor. What we find here, first up, is that across the board, reversing that final answer definitely increases the accuracy. So that's great to see. It is concerning because it means that we are kind of shooting ourselves in the foot or shooting these models in the foot when we write multiplication the way we usually do it. But it's interesting to think, is there a way to take our pre-trained text data, find all of those examples, reverse them, and then during inference reverse it again? That'd be pretty difficult. I don't know if it's worth it, but when especially when you can have the models just write some code, it makes no sense to do. But it is interesting, right? Furthermore, they looked at the actual number of attention heads, right? And they found that performance tended to really saturate at 3 attention heads. Whenever you had more heads than that, they basically ended up just doing duplicate operations as the first 3 heads. They only found really 3 fundamental tasks in the heads. Anything past that would just have the same attention pattern roughly as one of the first 3. Now, if we go look at here, this is the actual attention pattern of the heads. Each color is a different attention head. They made a combined pattern on the left for some reason. I thought that was kind of silly. I would have stuck with just the 3 primary graphs right here. Also keep in mind this is for the ordinal case, the regular way that humans write the ordering. But basically you can see that if you want to calculate the 4th digit of the answer, so what would that be? This is the ones place, tens place, hundreds place, thousands place, the 10,000ths place. You take as input, you do, what is this? D4 times D0 not. That was a typo. I think they should have had a little apostrophe here. They did not. I'm pretty sure that was wrong. But you take, first up, D4 is the largest digit of the first number, and then D naught prime, or we're gonna call it D naught prime, I guess, is the single digit to multiply it by, right? So to calculate this right here, that's the first thing you do is multiply those 2 numbers. That's having this attention head right here. It is multiplying that D4 by the D naught prime, hence the 2 dots that I have written down right here. Also, I wanted to point out that at the equal sign, interestingly, what it's doing is it's syncing its attention onto the multiplication sign. This model was only trained with this format with multiplying, so there's no reason for it to actually do anything here. It is literally just using the multiply sign as an attention sink, whereas if it were to use the other variable things, that would mess it up. So if you know about the attention sink concept, this seems to be an example of that happening. And I know it's been kind of iffy as if it's happening in the past, like if it's if the beginning of sequence token actually is that, but I think here is a pretty clear case. The equal sign attending entirely to the multiplication sign, that does nothing. That seems to me to just be an attention sink, right? Anyways, so to get out the 10,000th digit, first what you do is you multiply the previous digit by the single, by the bigger digit by the single multiplier, right? Or the biggest digit of sorry, I'm frazzled. The biggest digit of the big number inputs multiplied by the single number input, right? Then next thing you do, D3 times D naught prime divided by 10. That right here is his next attention head. This, I believe, I could get getting mixed up honestly, but this is the reason they do this multiplication is to figure out if there is any carryover task, if there's any actual digit to carry over, right? And then finally, the UCFC, the combination of figuring out if it should carry over, and this had a relatively more even distribution across the neighboring tokens of interest and the multiplier itself, right? And finally, they wrote in their formula mod 10, because we use base 10 obviously. I assume this is being done actually in the MLP, but I could be wrong there. It could also, I guess, be done in the uh, mixing output linear layer of the attention mechanism, but I would guess in the MLP, unless they did an MLP here, in which case it would be the actual output linear layer. Next up, we have the reversed case, meaning this is where we have the reversed final answer. You can see, compared to the ordinal one, the direction of the diagonal line and the attention mechanisms has in fact reversed. So really exact same algorithm happening here, but in reverse. We have the same setup. I think they should have made an effort to actually match up the colors to the actual task, but whatever. D4 times D naught prime, same thing here. D3 times D naught prime, same thing here. But the difference being that whereas in the ordinal case, the regular ordering, our UCFC was really iffy in here as to what it's attending to. Look how murky that all is. Very few actual dark colors, the way you have a dark color here, that dark color indicating a actual high probability in your attention mechanism, right? Whereas in the reversed ordering method, you see that the cascaded UCFC is less. The color is so annoying. So this green is the cascaded UCFC, right? And then this blue is it as well. Bigger paper, they really should have thought about matching those up. It's an easy thing to do just for sake of readability wise. Anyways, what you find is that it actually pretty heavily attends to here. The vertical line, I believe, would be in a, wait, no, the horizontal is the interesting one, right? It has to attend to pretty evenly multiple points in order to get out that A4 digit. And it attends to many points, reason being it has to look at the prior digit's carry amounts and look at the current digit's multiplication and decide how to carry over to the next digit, right? That's the operation it does. So it actually uses many digits across, whereas the other two tasks are pretty simple. They only attend to really one or two tokens, right? Two tokens, given that one of them is the to be multiplied by piece. Then there is, I believe, an issue with the attention in terms of the UCFC task. I need to check on this to confirm, but I believe it is the case that transformers really have trouble trying to attend to many tokens at once across, like, from to use many keys at one time for one single query. Uh, I believe reason being it just convolutes everything in terms of what's actually being added together, and it becomes very sensitive to the specific probabilities that actually come out. And this happens in the UCFC task. It seems to be a source of error. The models really kind of fall apart if they have to pay attention to any more than like three key tokens, whereas the UCFC task fundamentally requires attending to at least four tokens. Hence, that added error rate on top of the prior error rate from having to read off the previous heads or the other head results. And that, of course, I meant that in terms of the ordinal case, it was having trouble splitting attention across many different keys, and then it is still doing so many different keys here in the reversed case, but again, seems to have higher accuracy thanks to the ordering. Now, to emphasize this, different from the ordinal transformer, the reversed one has access to previously generated answer digits, right? So when it's generating its answer and it's doing first output, first digit, second digit, third digit, the ordinal one has to output the largest digit, right? Whereas the reversed one gets to output the smallest digit, the ones digit first, right? The ordinal one effectively has to think about and calculate every single smaller digit when creating its first and largest digit, whereas the reversed one gets to calculate just a single smallest, simplest digit that has no prerequisites, and then on the next digit, it can literally attend to its answer at the prior token, right? Hence why this green head, the cascaded UFC, actually attends to prior answers a bit, right? Coming out A4, it is attending to A1, A2, and A3. Sorry, this is the A3 token that will eventually be turned into the answer, the output of A4, right? And it is attending to primarily A1, A2, and then a bit as well to itself, right? Which makes a lot of sense for that task. Whereas this could not be done in the same setup for ordinal. You do not the when you have that A5 token, the largest digits place, the 100,000th or whatever it is, it has no ones, tens, hundreds digit already calculated to attend to. It just has nothing to look at. It has to effectively do all that on its own implicitly, as opposed to being able to go back and reference its prior answers on the prior digits. They did, when we said earlier, mess with number of attention heads right. It was not only that more attention heads end up with duplicate tasks, they just do the exact same thing as already being done, but when you have only one or two heads, those heads effectively end up to do trying to do multiple tasks at once, which obviously is not ideal. Now, all that was for a big number times a small number. Now we're looking at big number times big number multiplying, right? Which with this, there is a significant accuracy drop. So when our second number, the multiplier, is now 5 digits long, they compared across different regimes of whether to actually even use those digits. So down at the bottom, this is actually a number DDDDD is a number that actually is using all 5 digits that grabs some random numbers and use that as a multiplier. But then any zero indicates that that value is frozen at zero, meaning that this case right here reduces down to our previous task of big number times single digit number, right? Interestingly, they have a 2 digit number, 3, 4, the full 5, and a number where the middle 3 zeros were held constant and just the largest digit and smallest digit were used. And what we find here is that when giving out the answer could have as many as 9 total digits in the answer. What is that? That's a trillion, I think. It's in the order of a trillion, right? What they found is those middle digits across all of these settings have just terrible accuracy, atrocious. And it's also like the more middle you get, the worse. So these two, 9.9, 9.5, as opposed to more on the edge, 39% accuracy, 32% accuracy, right? The model is, at this point, at many of these middle points, when it hits 10% or so, really just guessing. A commenter on the chat just asked, does this mean LLMs can perform calculations better if we simply prompt them in Arabic or some other language with reversed number ordering? So yeah, if you were to pre-train a model in Arabic, and if you're saying that Arabic has a reverse number ordering, where the smallest digit goes first and the largest digit goes last, then yes, they should perform better. Big LLMs, as well as a single layer transform like this one, should perform much better on multiplication than they would in English with our big digit first, small digit last. However, doing this for English, for example, would be very tough to do. How do you go through your training data set and reorder all these cases? Not easy. Those results just now were the ordinal case, still low accuracy in the middle digits, right? The biggest digit and smallest digit, very high accuracy. Smallest one is easy to do, obviously. It's the very simple circuit right there. And the biggest one, and most of these tasks don't really count very well because they're just the answer is 0 for like some of these tasks. But even when in the case of where there actually should be a digit here, it's still relatively easy, the biggest digit number, because your only source of inaccuracy is a potential carryover from the middle numbers. Now, for the reversed task of again big digit times big digit, relatively same thing here. The middle is very difficult. The beginning and end are easier, but we do see overall, uh, same as earlier in the big digit times single digit task, that the reverse task is easier. Look at this 5.2% compared to 8.1, 0 compared to 0.1. Still tough. Big digit times big digit is still very, very tough, but it is a bit easier than the big digit times single digit. Now, as for why two big digits are still so tough, reason being that when you have one big number times another big number, that's a lot of compositional tasks in here. And remember, they are training a single layer transformer. That's the issue, right? It now has to do this this is its own set of like 2 times big number, aka big digit times single digit, as in like the previous setup task. But then you have to do it again for this 2, which is this row, and then again for the 4, meaning that when you have for your second number, a large digit version, you are effectively doing the already difficult task of the first part of this paper multiple times, right? A very, very compound task. These middle digits, especially, have the most compoundedness in there, hence the darker blue line, whereas the edges, very, very little. That biggest digit, all it cares about is 5 times this, and then maybe a carryover digit from the prior one. Now, the big issue being here that it is in fact a single layer transformer we are using, meaning it lacks the capacity to just across layers compound this task. Also, they said that, but there's other issues as well. Like, they specified that they have a 3-head transformer that they chose. It performed the best per compute or whatever. But they didn't specify like what the rank of the head was, for example. Are they working in a subspace or in the entire space? The norm would be subspace would be the dimension of the model divided by number of heads, but they didn't specify. And I don't think it would be a huge issue. It definitely is a lot less important than doing more layers, but it might be a thing. I don't know. Now, when they actually did go around and add layers, remember these are results from earlier table, but then on the right, the big by big digit, we do find that all it really needs is many layers in order to get accurate. Although the number of layers is kind of concerning. This is just multiplication, right? And it needs 2 layers. And not only that, keep in mind, this is 5 digit by 5 digit multiplying. It's not like 10 digits or like 100 digits or whatever it is, which a human can do. It's just 5 digit multiplying. We get all the way to needing, I'm gonna say 8 layers to, like, if you want care about like compute per performance. But if you want to actually like know that it's the correct answer, you need 12 layers, maybe 10 or something, to actually solve a 5 by 5 digit issue. This is an issue with transformers at large, kind of similar to the whole lack of ability to do recurrent algorithms issue. Is effectively the multiplication algorithm is in a way you have to calculate some sub piece and then use that sub piece to do more. It is like kind of recurrent in that sense, and it is an issue with transformers in that if you had not just a recurrent number, but one that actually was allowed to um, a chosen number amount of times repeatedly edit its answer until it finally settles on one token. I believe RWKV does that. I'm not sure though. I don't know much about that model. But you would need a model that effectively intelligently routes, intelligently decides how many iterations of this problem solving task it wants to do, which would be super interesting to see. But yeah, it seems like transformers are just not great for tasks that have this many compound tasks all together, as well as the ordering problem. Or obviously, it fixes that when you reverse things as well. It's just a very frustrating setup for transformers. They really are built for parallelizable tasks, not for tasks like this that honestly do require some recurrence. What they also did was they increased the proportion of simple samples, meaning fewer digits, and that brought about big accuracy improvements. Doing just the added depth of layers and the reversing only gets you so far to 8.7% accuracy, but you really need the samples, the more and more examples of low digit multiplication for it to do well. What's happening here is that the model, if it sees regular one digit times one digit more often, it will actually learn the how multiplication works, as opposed to just giving it archive as a pre-training corpus and it having to like off the bat do 5 digit by 5 digit multiplying, right? However, if they did test it out and they found that if they did too many simple samples, that did degrade the model's abilities because it just didn't see enough difficult ones. And a bit unrelated, but also want to point this out that they assumed like an actual reasonable tokenizer. A lot of LLMs today, this is less common now, but GPT-4 it's the case. I believe it's fixed in GPT 4.0, but I could be wrong. A lot of LLMs still use tokenizers that actually bother to tokenize the numbers, aka combinations of them, which is just a nightmare. Just not a good idea. I know Llama does not do this. I forget if it was Llama 2 or 3 where they fixed that, but I know by 3 anyways, they've definitely fixed that and they actually use individual digits when doing the multiplication and everything. But some LLMs are like have that extra hindrance on that just ruins the possibility of them doing well. And yeah, I believe that is it. Don't leave yet. If you got this far, you're going to love this video or this playlist. Don't forget to like, subscribe, comment, hit the bell, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, and consider supporting me monthly either through Patreon or by hitting that YouTube join button down below. For as low as $1 per month, you can get early access to my videos. Or if you're a one-time payment kind of person, hit up my Venmo. And if you want to borrow my brain for a bit, consider booking a paid consultation video call. All of those links are over in my link tree. And yeah, end of video.